If you've ever done any kind of coding, you're probably familiar with binary search. It looks something like this: a function that takes as inputs a sorted array, its size, a value to search for, and returns true if that value is found. The idea is to look at the middle of the array. If that's our value, then we just return true. Otherwise, if the middle is smaller than our value, then all the elements before the middle will also be smaller, because our array is sorted, so we can just ignore those elements. And we do a similar thing if the middle is larger than our value. This leads to a very fast search algorithm with time complexity order log n and a simple implementation, as you can see. I want to show you a completely different approach to implementing binary search. I found out about it while taking part in computer science Olympiads and being active on various online judge sites. People around me were saying that it's noticeably faster and encouraged its use in contests, and I just sort of took their word for it over 10 years ago. However, I wasn't able to show that it's any faster than on a modern computer and compiler. In fact, it was usually slower in my tests, depending on what optimizations I compiled with. I'm not sure if the speed up was an urban legend or the advancement of compilers in the last 10 years made it obsolete. If you're familiar with that kind of things, please leave a comment. Nevertheless, I think it's a really cool take on binary search, and I think that understanding it can make you better at understanding algorithms in general. There are always multiple ways to approach something, and you never know how the ideas behind some of the more obscure ways might come in handy someday. In this particular case, I think the algorithm I'm about to show you teaches us not to ignore the binary representation of numbers and to sometimes try to build our answer bit by bit, literally. So without further ado, here it is. I suggest you pause the video here and try to see if you can figure out how it works for yourself, after which I'll explain it by working out an example. Alright, so congratulations if you were able to figure this out yourself. So let's work out an example. Let's consider the array A containing the numbers from 0 up to 39 inclusively. So basically the values are the same as the indexes in the array. And we are going to search for the value 25, whose index is also 25, because this is how we built our sorted array. N is equal to 40, and now it's quite easy to see what this first while loop does. All we need to know is this operator, and this is a bit shift to the left, or a left shift. So it's equivalent to multiplying by 2. This was generally considered faster than actually doing multiplication in contest problems and online judge sites. Again, I'm not entirely familiar with why that is. However, I can tell you that for many problems, they actually were faster. So it's probably something to do with how they compiled the sources. But again, today, even if you replace with the multiplications and the divisions here, it doesn't seem to make much of a difference, at least in my experiments. Alright, so this while loop is basically going to end with step being equal to the smallest power of 2 that is larger than or equal to n. And in that case, that is 64, which is equal to a 1 followed by 6 zeros. Why 6 zeros? Or how was I able to know this so fast? Well, I knew this because 64 is 2 to the power of 6. And just like in base 10, 10 to the power of x would be a 1 followed by x zeros. For example, 10 to the power of 2 is 100, which is 1 followed by 2 zeros. It's the same in base 2 for 2 to the power of x. It's a 1 followed by x zeros. And it helps to write it out this way. Okay, we're going to also have I equals 0. And now let's take a look at this second while loop. So first of all, it's obviously going to execute because step is non-zero here. And the if condition, the first condition, I plus step lower than n, is not going to be true because step is 64. So it's going to get short-circuited, and this won't even be checked, and this won't be executed. So what will be executed is this. And this is a right shift, which is the opposite of a left shift. And as you may guess, it's equivalent to division by 2. Alright, so we will have here step divided by 2. And in the next step, 64 divided by 2 is 32, which is equal to a 1 followed by 5 zeros. Again, 32 is 2 to the power of 5. Now let's see if this gets executed. So I plus step is 32. 32 is lower than n equals 40, but a of 32 is equal to 32, which is not lower than or equal to 25. So the body of the if does not get executed. But we will again divide step by 2. So we have I remaining at 0, step divided by 2. Next, step is 16. Let's write it out in binary. Let's see now. So 16 is lower than 40, and this is true now. A of 16 is 16, which is lower than or equal to 25. So we will have I equal to I plus step, so that is 16. And we again divide step by 2. Let's do another step in detail. So step is equal to 8, which is equal to this in binary. And let's see. Again, this is always going to be true from now on, or almost always. So we have to look at A of I plus step. So we have to be careful here because I is 16 plus 8, that's 24. So A of 24 is 24, which is lower than or equal to 25. So the if body gets executed. We have I equal 24, step divided by 2. Next, step is 8, which is this. Now let's see. Again, this is true. We have to look at A of 24 plus 4, that is 28. And that's not going to be lower than or equal to 25. So the if body does not get executed, so I stays at 24, and step gets divided by 2. Step will be 2, and again it's quite easy to see that this won't be executed. This won't execute the if body, so I will stay at 24, step will get divided by 2. And finally, we have step equals 1. And I equals, if you execute this conditions, you will see that they are all true. We have here a of 25, which is lower than or equal to val, so I will be 25, and step divided by 2, which will make the while loop end now, because step will be 0. And finally, I is the index at which we should find our value. So we return if we did that, if a of I is equal to val. And in this case, of course, it will be, so it will return true. So this seems to work. You can work it out on other examples as well. You can also write a driver program that compares its results with the classic binary search on randomly generated arrays. I've done that. I can assure you that it's correct. But what's the idea behind it? We were able to quite easily execute its steps. All we needed to know are basically these two bit shift operators. But what's the idea behind it? We still don't know that. Well, the idea behind it is to compute the answer bit by bit, like I've said. And that's not just a figure of speech, it's actually what's happening here. If you look at what we've done here, I is built up by adding powers of 2. So we've added powers of 2 here, when we made it 16, here, where we made it 24, and here, where we made it 25. So that's what we do here. We compute the answer bit by bit. We see if the bit at any possible position needs to be made a 1 in the answer. And that's true for this position, and this position. And if you add these, just like you would add numbers in base 10 basically, you would get, let's see, so we have a 1 here, and we have to be careful here, 2 zeros before it, a 1 here, and another 1 here. I hope I didn't mess this up, but yeah, it looks to be correct. So that's our answer. You can transform this to base 10, and you will see that you'll get 25. So I think this is a pretty nifty little approach. Unfortunately, it doesn't seem to be faster, at least not today. But like I said, I think it can help us think about various problems in a very nice out-of-the-box sort of way. I hope you've enjoyed this video.